Hi, so in this last video, we're going to look into the branch and bound method and how it uses the notion of relaxations to find solutions for IPs. So the branch and bound method is based on this idea of divide and conquer strategy. Suppose we are interested in solving a problem of this form, and we assume that we can't find the problem as posed originally is just too large to be tackled at once. So basically what we do is we break the problem into subproblems that are easier to solve. That's an important part, by the way. And then what we do is we combine the solution of the subproblems to obtain a solution for the original problem P. So one way I like to visualize this is that suppose we are looking for a solution within this space called S. And what we do is we break S into more manageable subparts. So this being S1, this being S2, all the way to Sk, say. And what we do is we solve the problem here, we solve the problem here, we solve the problem there, and then we compare the solutions. So in this area, I found a solution xk1. In this area, I found a solution xk2. And then once I have a solution for each of them, I can look at them and think of a way they can be combined into a solution for the original problem. And combining can be something simple. It's typically something simple as, just pick the best solution between what you found for each of those. If you was, suppose you're optimizing the same objective function, you're just breaking your search space into smaller parts, and then you just compare the solutions you found in each of those parts, if you found any, and pick the best. So this is what we mean by, divide and conquer. And the working principle is basically what is behind this proposition here. So let us, suppose you divided your problem in k parts, and an important aspect of that partitioning process is that it has to be such that when you make the union of the parts, you recover the original problem S, or the original search space S. And if that is so, we call this a partitioning or a decomposition of S. Notice that we're maximizing here. So let zk be simply the max for each of these subproblems. So the solution we found in S1, the solution we found in S2, so on. Then the solution for the whole problem is as simply as picking the one you found. So it can be combined really simply. So that's a benefit of, and presuming that solving a subproblem, a smaller problem, is easier than solving the original problem. Actually, the premise is that when we break, an important premise behind it is that when we break these into problems like so, solving these parts independently needs to be cheaper than solving the whole problem. And that is especially the case when you have problems of complexity that is said to be exponential. Well, this is actually the case for other cases as well, but specifically, which is the case of branch and bound of combinatorial problems. It basically is telling us something that's like so, that if you think of this graph, where this is the size of the problem, and this is the number of, let's call it, how hard is to solve it. So the number of, you can think of this as the number of computational operations you have to perform in order to find the solution. This is what we see, is that very seldom we have things that behave linearly. It's particularly in the context of IPs. Most of the time, what's going to happen is that we're going to see things that behave like so, or even like so. So you see that if I compare these two in terms of how hard the subproblem is, it's clearly harder to solve a full space problem than solving its decomposition, if that is true. And these are the class of problems. These are the curves that you're going to see for the problems we're trying to solve. We call these the superlinear, or they increase faster than linearly in terms of the size of the input. So in order to control how we generating subproblems and making sure we're keeping track on the way they are generated, we use the notion of an enumerative tree. So these are the trees structures that you probably see in a programming course. It basically means that we have this notion of a main node that associated with them we have child nodes, and these keep being branched into children until you get to a point where there's not branching anymore, and that is what we call a leaf node. And if you think about this, it looks like the upper part, the canopy of a upside down tree. So the trunk will be here, I guess. So this is one example where we are opening an enumerative tree for a search space that is composed by basically 3 binary variables. So 1, 2, 3, that's X. And we're trying to figure out whether this is 0 or 1, whether this is 0 or 1, or whether this is 0 or 1. So basically what we're doing is we're breaking the first part is opening the tree into 2 subproblems. So, and opening a tree in a subproblem typically can mean things like fixing values. So we say on S0 we are fixing the first component to be 0 and leaving the other two to be decided. So you can see that in this case here, and likewise in the other side here will be all, instead of 0 you will have 1 here for all these. And then you can open this now looking at the second component, and if you open in the third component, then you have you don't have anything else to do, but you end up with these 8 leaves, each of the leaves representing a feasible solution for our original search space. Yeah, so that's kind of the structure we're going to use. By the way, this is not useful at all. Well, it is useful in organizing the solution process, but it's not useful at all in the actually process of finding solutions, because what you're still doing here is brute force enumerating all possible solutions. But the structure is very important for us. And just so we see that S0 and X1 and S1, they are a decomposition of S because their union returns S again. And this is how we're defining one being X is in S, such that the first component is 0 and the other is the first component is 1. And then you keep it, when you get here, you're assuming that the first component is 0 and the second component is 0. And here you're getting the first component is 0 and the second component is 1, and so on. So that's the structure of an enumerative tree, or simply a search tree. But the main principle behind branch and bound, the method, is not, if you're only doing branching and you have to investigate the whole tree, you're not doing anything special. What comes turns the search, tree-based search, into a powerful framework is if you have somehow ways to prevent that some of the branches needs to be explored. So if you think that instead of opening the whole tree, you can, in anticipation, preemptively decide that a whole branch can be cut, can be not explored, this filters out, this reduces dramatically, hopefully dramatically, the number of solutions to be investigated. And that comes from the notion of using bound information. Hence the bounding in the branch and bound. So let's see how that can actually work. This comes from this sort of general proposition that says the following. If you have a decomposition of your problem S, okay, remember that we're maximizing the setting, and we have the optimal solution for each of our subproblems, our decomposition problems. We're calling these subproblems, by the way. So now let this overline zk and underline zk be upper and lower bounds. In the context of maximization, that tells us in any context, that's telling us the following. Your dual bounds, they tend to have their quality sort of defined locally, because you can only impose a global bound to the original problem S by means of taking the max of these dual bounds. And that is okay, but that's not fantastic, because, this would be really powerful if that wanted actually the min of these upper bounds. And the reason for that is because these upper bounds, in the context of maximizations, they are dual bounds. And dual bounds, they are going to tend to be only valid locally, because the way you're generating the decompositions is by imposing constraints, like we did in the tree with fixed the value. However, the primal bound is global, because the primal bound is a feasible bound, and a feasible solution is feasible to S, so it works everywhere in your tree. So every time you find a primal feasible solution, you get a chance to update a global bound. And once you have this global bound available, you got a really powerful measurement that allows you to look at further branches and decide whether it's worth to carry on searching there or not. We'll get to this in a second. But the reason why lower bounds in this case are valid globally is because they are primal feasible. So they are feasible values for S. So they work for everyone. Dual bounds, on the other hand, they are artificially generated in the notion of branch and bound, in a sense that you're basically starting from a relaxation and constrain it over and over again. Again, think of the idea of fixing the x1s or adding subtotal elimination constraints. So these are only working locally, really, because they are based on information you just obtained from a relaxation that has a specific set of constraints added to it. Okay, and so with these local and global bounds at hand, especially the global bounds, we can preemptively in a sense, before you do anything, you can do something else. So preemptively hold the search through a given branch escape. So in our tree analogy, we are cutting a branch escape. So basically 3 situations will allow you for pruning. The really important one, which is what we say pruning by bound. And it basically is telling us the following. So we start with this large relaxation that we iteratively make it more and more fixed or more and more constrained. So that means that in that branch, the solutions you will obtain from that further constrained relaxation can only become worse, right? Worse again in a sense that if we're maximizing, this is our Z, so this is a space of the dual bounds, and we have, say, Z1, and then we generate Z2 by adding a constraint or fixing a variable value. So it's made worse in the context of maximization, but it's actually better because it's closer to this, okay? So if you happen to have at hand a lower bound, which is a primal bound, that is known to be greater than the upper bounds you're getting from that branch, it basically means that whenever that branch yields a feasible solution, that solution you're going to find is going to be worse than this, because this is locally our upper bound. And if the upper bound is worse than a global lower bound, you can see these things flipped. So this means that there is no reason to further explore this branch, and you can cut the search there and carry on somewhere else in the tree. We'll have a numerical example to demonstrate this coming up in the next slide. By optimality is just the obvious thing to do. That's, by the way, is a very deceiving sort of name. By optimality actually means it could be called by feasibility, because it just means that you found a solution that is feasible to your original problem S, meaning in this case, in the context of IPs, for example, being a solution that is integer, or if you're talking about the TSP, is a solution that yielded a tool. So this is one point. It's by feasibility, or because that solution becomes a candidate for optimal solution. And last but not least, by infeasibility, it might be so that you're constraining your search so much when you're dividing your relaxations that it might be so that you turned it infeasible locally. So here is a little example to see what's going on in that. So we're going to use this sort of notation to represent our search. So S is the subproblem we're solving. In this case, the main problem. You can even, sometimes we call this S0 instead to differentiate it from the original S. But that is basically the relaxation on the original problem. And so this is showing that we solved it. We are, in this case, because our dual bounds are upper bounds, that means that we are maximizing. So we don't have a lower bound available yet because we don't know any primal feasible solution. But this is our dual bound we obtained, 13.4, and that's the solution we obtained. It's a two variable problem, so we found 3 and 2.7. So one way in this case to generate potentially feasible solutions for the original problem is, applying this rounding mechanism here that we're going to look in detail in a minute. But we generate two subproblems, say 2 and saying that this number is either less or equal than 2 or greater or equal than 3, in the hope that we can find a solution that is not fractional. And now I have two subproblems I have to solve that I know nothing about it, so I decide I solve S1. So it can be so that when I happen to solve S1, I end up finding a integer solution, which was what the original problem was, meaning that this is feasible for my original problem. So therefore, locally I have this upper bound of 11, and because it's integer, I just got a local lower bound as well that is 11, because the solution is integer, so it's integer feasible. And then what happens is, because the lower bounds, the primal bounds, are generalizable, they are global bounds. It means that I can use this bound and send it there and send it there. So all my subproblems get this global lower bound. What I'm looking at know that is greater than equal than 11, wherever I am at the tree. So now I'm at S2 that I haven't solved yet, and the only thing I know is that I have this bound. I can't hold a search here because this solution is 11, but it doesn't mean that there might be an integer solution here that yields me something that is, I don't know, 12.5. So until this gap is closed, I have to keep exploring until I can, fully clip all the tree. And so I go about and solve S2. And then when I solve S2, I notice that I get a dual bound that is 9.7. That was after I added this constraint. So a dual bound of 9.7 with a fractional solution here. So the first reflex we would have, well, this is fractional, so I have to carry on and, generate further nodes. But if you look, because we solved this first and we had this lower bound available, this yielded a solution that was 11 in value. If I carry on exploring this, I can guarantee you that no solution that is going to come from here is a solution better than this, because this is an upper bound locally. So it might be so that I keep opening up and solving and eventually get a solution that is 8 or 9 perhaps. But I already know a solution that is 11, so that solution will be suboptimal anyway. And the reason why I know all that is because the solution yielded me a lower bound, a global lower bound, that is greater than the local upper bound of this. So I can halt the search here and say that, look, there's nothing that's going to come from that. This is pruned by bound. So that's basically the two mechanisms. Well, there's pruning by infeasibility, and just means that when I added these constraints, I made the problem infeasible, so I can prune as well. So one thing that you might be, asking yourself, where those constraints come from. And so basically they are associated with branching bounds specifically for IPs using LP relaxations. So this is just a summary of, before we go there, just a summary of the how we prune. So we're solving these relaxations on SK, and if the solution of the relaxation is optimal for the subproblem, we prune by optimality, and meaning that it's not that it's optimal for the subproblem, but it's feasible for the original problem. That's the main point. If the relaxation is infeasible, we just prune by infeasibility. And if it is so that the solution is worse than a known primal bound, we can prune by bound. And otherwise, we'll have to perform branching. Right? So, like I was saying, what we're going to be looking into is a branching bound algorithm that is geared towards solving IPs. And for solving IPs, the most common and the most widespread is that is a LP-based. So it's an LP relaxation-based branching bound. So the relaxations we're going to be solving are LP relaxations, and we'll have to devise specific mechanisms for branching that are going to be concerned about fractional variables. So in an LP-based branching bound, what you do is you start a LP relaxation that gives us dual bounds. And then whenever we need to do branching, our branching is based on the fact that whenever you have a fractional component on a variable, you can yield two subproblems. You can break your search space into two by saying that you either have to look at a child in which that component that is fractional is either less or equal than the floor of the value, the round down value of the variable, the component. And another one is that you are, so this is wrong, is greater or equal than the CL or the roundup of that value. It goes like this. So, suppose we are, so this is our S, where we're trying to find a solution. And we got to a point where, say, we found this point here, which has this integer coordinate, but this is a fractional coordinate. And basically, we're creating a division in our divide and conquer strategy. You'll say, you know what? Search on this side or that side. Because I know that in the between, there's not going to be any feasible solution. So this is how we break our search space into parts. Right? Now, of course, it might be so that you don't have a single fractional component, and to select which of those fractional components to devise this branching it can affect performance. We'll see that there are some ways that you can specify them, but there is no winning strategy that's good for all problems. Basically, what solvers do is that they give you a range of possibilities that you can choose among you think is best for your problem, and many of them have predefined optimal or automatic ways of figuring out what could be the best in a specific context. Another idea is how to select the next subproblem to solve. You can see that the order in which you solve these subproblems is quite impactful, in the sense that we've seen in that small example that we had here, that the only reason I could prune this is because I solved S1 before. But it could be so, but I had this strategy in mind that I wanted to go as deep as possible first. So I could have started solving this and started on the right because, I don't know, I'm right-handed. So I'll solve this subproblem first. I wouldn't have this bound here. So I would have to get this variable and then branch and then perhaps solve this subproblem because I like right better than left. And that would mean that, I will have to carry on solving for a while when had I solved this before, I would, do this branching and prevent the solution of several LPs. So that's the order on which we solve these things is also very important. And again, solvers have a few ideas, a few methods that you can choose from in order to select how to define how to select the next subproblem. And there are also some automated ways in place that try to define what's best for the problem at hand. And depending on, typically, this is the branch strategy that you're going to see most of the time, if not all the time. But in some specific contexts, there are alternative ways to perform branching. But as a general rule, this sort of fractional branching is what you're going to see. All right. So here is the very small numerical example so we can wrap up. So this is the same problem we've been looking into since the beginning of the lecture. And how would branch abound work on this? Well, we would start solving this LP relaxation, which would return for us this solution. And once that is available, then we can assemble our first node. Our first node is such that we don't know any primal bounds for it. This is the dual bound we just got. And that solution here is a solution where x1 is fractional and x2 is 3. All right. So from here, this is not a solution for the original problem. So the next thing to do is to perform branching. So how we go about branching it? Well, we look at the variables, see those that have the x to see which are the fractional components and pick one to branch on. So we're going to choose that because that's the only fractional component. And 20/7 is just shy of 3. So it means that we are breaking this into a 1 to a subproblem in which x1 is less or equal than 2 and another one where x1 is greater or equal than 3. Because that adding this constraint is basically going to make my search space be constrained on this side for a subproblem and on that side for another subproblem. So I'm basically getting rid of this part in one of the subproblems. So this is how we're going to perform our branching, creating the following subproblems, and our tree now looks like this. All the current leaves that we haven't been pruned yet, they are basically subproblems yet to be solved. Right? And we typically, in the implementation of branch abound, we keep them on a list, which we're representing with this fancy L here. So that list of subproblems that are yet to be solved, in this case, will be S1 and S2. Because I haven't solved them, there's nothing I can conclude about it. So the next step would be using a subproblem selection strategy to look at this list and pick either S1 or S2. And of course, the way you choose them, can influence the performance of your method. So let's pick x1, and that would lead us to the following situation. Remember that S1 is my original problem, so basically it's these 3 constraints from my original LP relaxation plus this constraint that says that x1 is less or equal than 3. So that leads me to this new LP relaxation value here, which is integer in x1, but is not integer on x2. So because this is not integer, I just get a dual bound of 7.5 with 2.5 as a solution, right? So the next step to do here would be I can either solve S2 or carry on and solve one of the new subproblems. You can see immediately that the subproblems here are going to be one with a constraint x2 less or equal than 0 because it's 0.5, or we can simply say equals 0 because x2 is constrained to be greater than or equal than 0. And in this case, we'll have x2 greater than or equal than 1. So we will be generating a subproblem, say S11, that wants things to be less or equal than 0 or equals 0 for x2, so it would be this feasible region, basically. And for x2 greater than or equal than 1, we will be wanting things that are above this line. Okay. Right. So this is how we generate our new subproblems. And now our list of active subproblems become S2, S1, S11, and S12. And again, I have to apply a problem selection strategy to decide whether I'm going to solve S2 now or whether I'm going to solve S12 or S11. Okay. Let's assume we solve S2. And S2 is a problem that can be pruned by infeasibility, because if you see, the constraint that is added to generate S2 is, so S2 is the original LP constraints plus this constraint with things to the right. Right? So that means that there is no feasible solution that is within this polyhedral set and on the right of this constraint. So it's infeasible. And there's no exploration to be done there, which is great. So now we have to select a subproblem between S1 and S2. Suppose we choose S2, S12, sorry. And then when we solve it, it has an integer solution. So our x is 2 and 1. That is integer. So this is the local upper bound it generated, and it turns out that it gives me also a lower bound, which is global. So what I go about and send this lower bound there, there, and there. See? And because this is, there is still, would be still a chance that this could yield a solution that is, say, 7.1 or 7.2, which would be better than this. It still means that I can't really prune yet and have to solve S11. So when I go about and solve S11, I obtain this value of 6. I should have put this. This here would be x. It would be the solution of this. So let me draw here. This is S, the feasible region S11 is when I want x2 to be 0. And would be this point here, which x1 is 1.5. And remember that's the objective function at 4 times x1, and that's why 6. So this one here is 1.5 and 0. So I solved S11 and obtained a dual bound of 6. And that basically tells us that because I solved this first, then I had a primal bound, that it happens to be greater than this dual bound in a maximization. That means that I can prune this by optimality, and I don't need to carry on branching on this. Again, had I didn't solve this before and didn't know about a primal lower bound, I would, in principle, have no reason to believe why I shouldn't carry on, and could probably branch on this. Will branch on this and carry on solving more and more LPs. But once we got here, then the tree is fully pruned. The list of feasible problems to solve is empty. So the next step is to basically look at all integer solutions I generated and pick the best. In this case, we only generated one, so this is the best one we have. So here is to wrap up a pseudocode of what would be a LP relaxation branch and bound. We are assuming that we're solving this problem S that has a formulation P formed by a collection of linear constraints. So we start by initializing the list with the original relaxation, and we just say that our lower bound is minus infinity, and have a solution. We call this the incumbent solution that just stores the best solution found so far, and it's filled with garbage in the beginning. And while the list is not empty, what we go about is we select a subproblem here to solve. The first iteration, we have to solve the only subproblem that is there, which is the relaxation, and then we remove it from the set. And then what we do is we solve the LP relaxation of this subproblem, obtaining a lower bound, a linear relaxation Z and a linear relaxation X. This is automatically a local upper bound. It's a dual bound, so we can update this. These are our tests for pruning. So we're trying here to prune by infeasibility. If that doesn't work, I try to prune by bound. And if that doesn't work, I check if I can prune by optimality. And notice that if I do prune by optimality, meaning that the solution I found is integer, then I immediately update my global primal bound. And I basically say that it is the largest between what I found so far and this local upper bound that are just being found that happens to be integer. See? And I make my my solution, and I make my X bar this incumbent solution. This is a bit poorly noted, but it only makes sense to make to keep an incumbent solution if this was the case. If that solution you found is just worse, just keep the best solution you found. Then if everything else fails, then it means that you have a fractional component, and then you're going to create your subproblems, one of them with rounding down and the other then with rounding up, with greater than equal, of course. Okay, and then you update your list of subproblems by adding these newly created subproblems and rinse and repeat. So that's it. That's branch and bound for linear programs. Well, for integer programs using LP relaxation. I hope that example had helped clarify how it works in the context of IPs. And other than that, I'm looking forward to seeing you in the session on Thursday. Bye-bye.